let's first briefly recap the history of transformers, right? So nowadays, transformer with self-attention mechanism has become a new norm in natural language processing, as you can see from this figure. So from the earlier stage, we have the AMO, which is just 94 megabyte, but gradually we have seen a lot of very giant models like the GPT-3 or even the Switch C from Google. So all of these models actually have a gradually very large kind of model size and also achieve significant progress in terms of the performance as well. So the significant improvement does not only occur at NLP, it also inspired a lot of vision and language work since 2 years ago, starting from the video bird, and we have seen a bunch of works on vision language pre-training like Wearber, TextMert, and Oscar, Venver, and to the most recently Clip and Elan. So we have also seen a very similar trend as in NLP to increase the model size of the vision language transformers and also the training data size of the transformers. So currently, we are also witnessing a clear trend of applying transformers to pure vision problems like image classification, object detection, and segmentation. So at the beginning, people usually try to plug self-attention layers into convolutional networks, like, for example, in a non-local convolution layer and the attention augmented ResNet, etc. But most recently, a variety of works are trying to replace the convolutional network with transformer layers. You can see from this part, we have seen a lot of works emerge in the last half year, especially I think we have already noticed a bunch of nerve submission, which work on the vision transformers from different perspectives. So at this point, a natural question is, what makes a vision transformer different from the convolutional network? Well, I would say there are many differences. So from my point of view, the first main difference is that vision transformers can model long-range interactions flexibly. So you can see here, the convolutional network has a hierarchical architecture, and at each of the layer, the model just see a part of the input. And with the increase of the layers, the later stage will have a larger receive field so that it can cover larger image regions. But the visual transformer is acting totally different. So given an image, the model first split the image into a number of patches and then project these patches into separate different tokens. With this transformer encoder, it will model both the local and global dependencies across all of these patches so that at each of the layer, the model can model both the short range and the long range visual dependencies. So the second obvious difference is that transformer has a dynamic and flexible self-attention operation. So in terms of the dynamic, we can see here, given the input and the gray square, the CNN actually is doing a sample independent computation. So no matter what kind of input value is given, then the CNN, the convolution layer always perform a convolution on top of the input with some predefined feature. But the vision transformer is doing some sort of sample dependent computation. It will extract tokens from the input and then compute the query key and value, and then follow up by a multi-head self-attention. So besides the adaptive computation, it's also flexible in terms of selecting which tokens to perform the attention. For example, for self-attention or transformer, it's pretty flexible to extract the gray tokens scattered inside this input feature map. So it's pretty simple to do this by gathering these tokens and also add some absolute position bias or relative position bias to each of the tokens for the self-attention. So this information differences do not necessarily mean better performance, right? So a follow-up question is, what make a vision transformer work? I would say the performance of the vision transformer has a low floor but high ceiling. So you can see here from the left side, we can find that. So the DIT model paper showed that with enough data augmentation, the performance of the vision transformer will be significantly improved over the baseline model. And also with enough and smart regularization like draw paths, the performance of the vision transformer will be further improved. And this will lead to a much better performance for the vision transformer in compared with the ResNet counterpart. And the similar trend was also observed in another paper called VisFormer. So the base setting just do not use any fancy augmentation or regularization. You can see here, the ResNet actually outperform or significantly outperform the DIT model without any regularization and fancy data augmentation. But if we add the information data augmentation and regularization to the vision transformer, then the performance will be significantly improved and surpass the ResNet 50, even with the elite setting or with the fancy documentation in the same manner. So this means that the performance of the vision transformer is starting from a low floor, but will reach a higher ceiling if we have enough data augmentation, if we have smart regularization. So another thing I would like to highlight is that it's pretty scalable for supervised and self-supervised learning. This is a paper from Google, Scaling Vision Transformers. I'm sure all of you guys already know this paper. So from the figures, the authors have already showed that, okay, if we increase the model size and the training data, for example, the small model, just a very small model, and then it increased the model size to a giant model. And similarly, it's increased the training data from 30 million to 3 billion. And you can see here, the basic model, the Hive can reach above 90 top one accuracy on image in the 1K, which is pretty high, right? So in spite of this kind of advancement in vision transformer, so is there still some challenges for the vision transformers? First, how to model the long-range interactions for high-resolution input, because we need to consider both efficiency and the effectiveness. In terms of the efficiency, we needed to think about how to cope with the quadratic complexity of self-attention for high-resolution input. In terms of effectiveness, so we need to think about how to gain the better performance for various vision tasks besides the image classification. For example, we need to think about whether we can achieve a better performance for object detection, for segmentation, etc. The second challenge is that how we can adapt this vision transformer to self-supervised learning, because almost all of the self-supervised learning methods in computer vision are using convolutional network. And till now, we have seen a few works are using the transformers, including our own works, EsViT. So more specifically, we need to think about how we can break the barrier between the NLP and the CV, because NLP domain, we have seen a lot of success and great work to scale up the self-supervised learning. So in this talk, based on this motivations, so we cover two works. The first one is a focal attention for local global interactions, and this is mainly for the supervised learning. And the second work is EsViT, which is for short of efficient self-supervised vision transformers. As the name shows, that we are working on the self-supervised learning for pure vision data. So I will first cover the focal attention for local global interactions. So this is a joint work with a lot of collaborators, and it also has been accepted by NeurIPS this year. So let's first discuss about the motivation behind our focal attention. So the first motivation is that, as we discussed earlier, Vision Transformer is good at long-range interactions, right? So the vanilla Vision Transformer actually can model the global interactions between different patches, but the challenge is that it is not good at coping with high-resolution input for dense prediction tasks. Imagine if you enlarge the input image, and if you increase the number of tokens, then it will be very hard for the transformer encoder to model the global interactions across all of the tokens very efficiently. And fortunately, we have already noticed a lot of hierarchy and the multi-scale architecture design in convolutional network. For example, the FPN and also the HRNet. All of these works actually have some very smart design to cope with this high resolution with the convolutional layers. So the question is that whether we can transfer this hierarchy and multi-scale from the convolutional network to a Vision Transformer. So based on this, so probably you can think it's maybe enough to do this kind of high resolution processing. But the problem is that even we use this kind of hierarchy and multi-scale architecture, so it's still not efficient enough to cope with high resolution input. So let's assume that there is a detection input like with resolution of 800 by over 1000. Then at the first stage, the input feature map still has very, very high resolution. For example, here it will be 200 times over 300. Then this is still a disaster for transformer layers to perform the global self-attention because of the quadratic complexity with respect to the input token numbers, right? The good thing is that there are some prior works based on the Vision Transformers are coping with high resolution input. For example, there are at least 3 works which are the PVT, Vision Transformer, and Vision Longformer. All of them are already accepted by ICCV this year. But there are some differences across different papers. So the PVT is mainly used a coarse-grained long-range interactions in the model. Briefly, they perform the coarsening for the key and the value feature map to reduce the number of key and value, so that for each of the query, it will just attend a small number of query and then compute the attention. In this way, it will significantly reduce the computational cost. But different from PVT, Vision Transformer and the Vision Longformer actually chose to perform a fine-grained short-range attentions. So this kind of short-range attentions are performed inside non-overlapped or overlapped sliding window. And here the Vision Transformer is performed on the non-overlapped sliding window, but with a shifting trick. And the Vision Longformer is performed on the overlapped windows with like the convolutional, like a convolutional layer. So both of them actually are trying to coping with this problem. And these two actually you can see these two are located at the two extreme of this spectrum. So focal attention is trying to achieve the best of both worlds, which means that our focal attention is trying to combine the coarse-grained long-range attention and also the fine-grained short-range attention. But this way, we can leverage the potential of the Vision Transformer, which are good at perform the long-range global interactions for all of the input. So actually, as described by some literatures on psychology, human vision also has some kind of focal attention mechanism. So in the human brain, so we have different neurons, and also we have a focal mechanism associated with the neurons to cope with the different visual input. And also we will have the focal attention so that we can zoom our own eye to look at the details at some regions, right? So this kind of focal attention in human vision actually can be illustrated by an image like this. So give the input image of a kite. So if when want to look at the cat nose, and then naturally the other regions far away from the nose, when we look at the nose, will blur out in our view, something like this. And also if we want to look at this cat leg, then okay, so the other regions will be blurred as well, because we will focus on this region, and the other regions we still know about the other regions, but we cannot capture details about other regions except for this region about the leg. And likewise, if we move our focus to the grass or the background, then okay, so maybe it's blurred for the cat. So inspired by all of this previous work and also the previous psychology experiment, we propose a focal attention operation. So this focal attention operation is performed to extract the visual input at a different granularity. So let's use this example, this image as example. So giving a query patch, the blue square, and then we attend the other patches surrounding this blue patch at the finest granularity, which means that we will use the same granularity to this query token. But if we go far away from the query token, we will causing the visual input with larger window, and in this way we can still capture the information, but in coarse granularity. We can further increase the distance between the query and the key or value token, and also we can increase the window for the coarsening, right? So by this way, we can gradually increase the distance between the query and the key or value. And also in the meantime, we will decrease the granularity from the fine to the coarse grain. By this way, a good property for this focal attention is that, so compared with the regular self-attention, if we use the same number of tokens for performing our self-attention, then the focal self-attention or focal attention will have much larger visual fit in comparison with the regular self-attention. So, but you can see here, if you count the number of the tokens in this region, so it's still not like, okay, so you count the region with the same granularity as a query, right? So based on this, I would like to use this figure to show how we implement our focal attention. Given the input feature map with size 20 by 20, so let's say we have a query token at the center as shown by the blue color, and then we gradually enlarge the region to extract the surrounding tokens. But the practical problem behind this implementation is that, so it has a low theoretical cost, but it has a very high practical cost, because we needed to extract the surrounding tokens and performing the coarsening for the surrounding tokens for each of these 20 by 20 tokens, query tokens, right? So based on this, we propose to convert our token-wise focal attention into a window-wise focal attention. In this way, the window of tokens, for example, these 4x4 window tokens, will share the same surrounding between each other, instead of, okay, each query token, each individual token share the same surrounding, right? But this way, we just spend less computation or operations to extract the surroundings for each of the window instead of the individual tokens. So as a result, we can achieve relatively low theoretical cost and also the low practical cost. Based on this window-wise focal attention mechanism, so I would like to use this figure to illustrate how we can perform the focal attention at different levels. So let's say we are giving the center query patch window, which contains 4x4 tokens. At the first level, we will extract a 8x8 surroundings for this query. And at the second level, we will enlarge the receive feed to cover more tokens. And at the third level, we will further enlarge the receive feed to cover more tokens, which actually is equivalent to the whole feature map. And given these three levels of receive feed, we will perform the sub-window pooling to capture the information at different granularity. So for example, for the first level, we simply copy it because there is no need to perform the pooling for these most fine-grained tokens. But for the second level, we needed to do the sub-window pooling for each of the 2x2 windows. By this way, we will obtain 6x6 quotient tokens. And for the third level, we will perform the sub-window pooling for 4x4 windows. By this way, we will finally obtain 5x5 quotient tokens. And this quotient token has more quotient granularity than this one or this one. And based on this, we will concatenate them together and then compute their value and key. Given this value and key, we will perform the attention, multi-head attention for this query, 4x4 blue tokens. And finally, we can update these 4x4 blue tokens by considering both the information inside this window and also the information outside this window, which are far away from these query windows.
Jianwei, sorry, I have a question. You mentioned that in the standard self-attention, there is a quadratic complexity with respect to the number of tokens. Can you just elaborate on the computational complexity of this focal attention? Is it linear?
Yeah,
linear complexity?
Yeah, that's a good point. So still, this is has a quadratic complexity, but here the focal attention will reduce the number of tokens, as you can see here. So let me show this figure again. So if we want to cover the whole image, so we need to use much larger number of tokens with the self-attention, with a regular self-attention. But if we want to cover the whole image, for example, here, we probably need need much less tokens for our focal attention, because our focal attention will has a more and more coarse-grained granularity for the tokens which are far away from the query token. So by this way, the token number will be significantly reduced, but the complexity itself is still a quadratic complexity with respect to the number of tokens.
I see. Thank you.
Yeah. Thank you. Yeah. Please interrupt me if you have any questions. So based on this focal attention, we design a multiscale focal transformer architecture. And here we only replace the self-attention with our focal attention to verify the standalone effectiveness. And we compare our model with the previous state-of-the-art Vision transformer. So we keep almost one of the architecture the same, except for we replacing the window-wise self-attention, which are performed inside each of the window with our focal attention, which perform the attention inside the window and across the different regions. So based on this focal transformer, so we first verify its effectiveness on image classification task. So we design our focal transformer in small, medium, and big sizes and run experiment on ImageNet 1K. So as you can see here, the performance is consistently better than the other models like the ResNet, like the PVT, Vision Longformer, and the SViT. So this means that our focal transformer actually outperformed both the convolutional counterpart and also the vision transformers consistently. So we further show the learning curve for our focal transformers and the perverse swing transformers. You can see here for a focal transformer, actually it has a much faster convergence speed, even though finally the gap will be smaller than the beginning. But you can see here the performance of the classification on ImageNet 1K are increasing much faster at the beginning than the perverse swing transformer. So we suspect it's because our focal transformer at the very beginning can already cover a long range interactions between different regions. But the swing transformer at the beginning is just performing the window-wise attention. And with the training proceeding, both of these kind of transformer can link to capture the long range interactions at the latest stage. So the swing transformer finally still works not that bad, but again it underperforms our focal transformer across different settings. And we also evaluate our model on object detection using different detection methods. So we test 4 different detection methods, including cascade mask assaying, ATSS, read-point V2, and sparse RCing. So you can see here we testify 3 different architecture: the ResNet 50, the swing transformer tiny, and our focal transformer tiny. You can see here we observe a significant improvement over the swing transformer counterpart across all of the detection method. So it's you can see here the smallest improvement is still 1 MAP, and 1 MAP for object detection actually is still significant enough. So finally, we'll enlarge the model size of a focal transformer, and then we compare our model with the SOTA number. So basically, we train a model on the ImageNet 22K, and then we fine-tune this ImageNet 22K model on object detection and also the semantic segmentation for AD 22K, 20K, sorry. And then, as you can see here, we testify different detection methods. The first one is HTC++, and the second one is dynamic hit. For both of these methods, our focal large model actually outperformed the swing large model as shown here. And we are observing similar trend for the semantic segmentation on AD 20K. So with this good performance, we further inspect our focal transformers and ask ourselves, do we need both short and long range interactions? So the answer is yes. As you can see here, the global attention and the local attention are combined together. In this case, the performance will outperform the other baseline method. For example, if we only perform the attention inside the window, then the performance actually is very poor. And if we add the short range surroundings into our focal attention, then the performance will be improved for both the image classification and the object detection. And if we only use the long range attention and add it to the window-wise attention, then it also improve the performance. Finally, if we combine together, then it achieves the best performance, which indicates that both short and long range interactions are important for both the image classification and object detection task. So we further draw a curves for our different type of attentions. So given the focal transformer tiny model, we draw 3 curves for the attention scores for the local attention inside the window, and the local short range attention outside the window, and the global long range attention outside the window. As you can see here, at the beginning, the green line is higher than the 2 other lines, which means that at the beginning, at the early layers, so the local attention actually is very important. So the local tokens are more likely to attend their close surroundings instead of very far away regions, because if it's very far away, then the visual dependency actually is very weak across different tokens, right? But gradually, if we look at the later layers, for example, the 4th layer, you can see here, or even the 5th layer, you can see here, all of these 3 type of attentions actually are balanced. And then if we further go to the upper layers, and then the global attention, the long range global attentions actually will dominate their focal attention. So by this way, you can see the local and global attention actually are dominant at the different layers, and they are working together to have a both global and local attention to achieve the best performance. So finally, I would like to show some visualizations of the relative precision bias length in our focal transformer. So this is a focal attention formula. So basically, it's pretty similar to the regular or conventional self-attention, except that we add a relative bias inside this supramax computation. So this relative bias actually consists of different parts. One is that it's for just the window tokens, the tokens inside the window, for example, 7x7 window. And the other part is between the tokens inside the window and the tokens outside the window, no matter which granularity levels. So you can see here at the first stage and the first layer, the relative precision bias length from our focal transformer actually will attend both a very long range regions, and also there's some other hits focus on the center, which means that focus on the most closed regions. And we are even see there's some very interesting pattern length for this relative precision bias. This looks like a cross shape for the relative precision bias between the attention of the tokens. So at the second layer, it's even interesting to see that there is a black hole on the map, which means that the model has already successfully learned not to attend its closed region, because maybe there are already a lot of redundancies between the query token and the most closed target tokens, but it will attend more around the window which are far away to the query windows. This looks very interesting pattern to observe as well. So similar patterns have been observed at other stages. For example, the second stage, so we have 2 layers. The first layer has 6 hits, and the second layer also has 6 hits. So for the first layer, you can see here, almost all of the hits are attempting to attend the tokens far away from the query. But for the second layer, it will attend the tokens which are relatively closer to the query, but still it's pretty far away, because each of these square means 7 by 7 tokens. So overall, these two collaborate with each other to capture both the far away visual dependencies and the short visual dependencies. So to summarize, I would like to put some takeaway messages here. So in our focal attention work, so the main contribution is that we proposed a focal attention which effectively model both the short and the long range visual dependencies for visual input. And our focal transformers based on the focal attention outperform the state-of-the-art vision transformers on 3 of core vision problems, including image classification, object detection, and semantic segmentation. And finally, based on our application studies, we found that both short range and the long range attention are important for the basic performance. And to hit up, so recently we are also developing a faster version of focal transformer because as I mentioned earlier, even though we convert the token-wise focal attention into the window-wise focal attention, it's still not that satisfactory to us in terms of their speed. So that's why we are also work hard to developing our second version of focal transformer, which are much faster than the current version and also achieve comparable or even better performance. So this basically
perhaps moving to the next paper, we take
sure.
some questions. Alexander, it seems you have a question.
Thank you. I have 2 questions. The first one, is it okay to suppose that we don't need anymore to use Swin, and so we should use the focal transformer as a backbone, so there is no drawback to use your focal transformer? Or if so, what are the drawbacks? And my second question is for other tasks like key point detection, pose estimation, are these backbone effective or not?
Thanks, Alexander. So that's a very good question. So to answer your first question, so if using focal V1, so because I'm introducing focal V2 as well. So if our focal transformer, so that I just discussed, actually is slower than the Swin transformer, even though it's achieved better performance in comparison with the Swin transformer. Even I'm the author of focal transformer, I still think it's very hard to replace the Swin transformer with the current version because it's not that efficient enough compared with Swin transformer.
Okay, but so at the inference time, you mean?
The throughput. So actually, I did not show here, but the throughput actually is lower than the Swin transformer, even though it's achieved better performance. So I can add one more comment here. So the main reason for this slow in throughput is because we need to extract these surrounding tokens with, for example, their rolling and unfolding. All of these are very inefficient operations in PyTorch, and then this will cost a lot of time and add the overhead to our original focal transformer. So that's why we are developing focal V2, which totally get rid of this kind of operations. And from our current experiment result, actually, it's pretty promising. So hopefully we can, we can have a focal V2 in the near future. And then in that case, I will definitely answer you with yes. So maybe
But
Focal
that
V2, yeah,
V2 is
yeah.
not yet public.
Exactly. Yeah, yeah. It's
Okay.
not public. Yeah, but yeah, it will be very fast, very quick. So
So-
with Focal V2, yeah, it's probably very safe to replace the swing transformer. Yeah.
Okay, thank you. And for my
Yeah.
second questions?
Yeah. So
Question?
for the second question, you were asking, okay, whether it can be applied to the key points detection, right, or post
Right, like
estimation, right? Yeah.
exactly.
I did not try a focal transformer on this task, but as you can notice from our previous result on semantic segmentation, I do not have any kind of reason to suppose that our focal transformer cannot work on post estimation because it supports the high resolution input, and also it can model both the fine-grained local interaction and the coarse-grained global interactions. So I would say it definitely performs better than swing transformer based on one of these results for the dense predictions. So, but yeah, I do not try it on post estimation, but yeah, I have a strong belief on this. Yeah.
Thank you. Thank
Yeah.
you.
Yeah.
Do we have more questions in this part? Thanks for the question. Just to add the comparison with the swing transformer, do we have this shifting window similar to swing transformer or not?
Oh, no. Yeah, that's a very good question. Actually, in our paper, actually, we compared we compared this. So basically, we did a Bayesian study. So for swing transformer, we keep the original architecture using the window shift, and we remove the window shift for swing transformer. And for our focal transformer, we add a window shift to our current design. Then we have four different numbers for both the classification and the detection. And our observation is that, so for swing transformer, if we remove the window shift, it totally ruin the performance, ruin the model. So the performance will drop significantly for both the classification and the object detection. But for our focal transformer, if we add the window shift, it even hurt slightly the image classification, but it will very manually improve the performance for object detection. So by this way, we conclude that our focal transformer do not need any further window shift because it by naturally already model the communication, right, between the tokens inside the window and the outside the window in a relatively efficient way. So there is no need to do the window shift anymore. Yeah.
I see. Thanks.
Yeah. Yeah. Thank you. Okay. All right. So yeah. So the second work is about Self-Supervised Learning, which is called EsViT. So this is the work led by Trey Yuan, Lee from the same group of men. So the first question we would like to ask is why we needed the Self-Supervised Learning, right? So basically, we want to leverage big unlabeled data to learn universal representation for a large range of downstream tasks. So nowadays, data is everywhere on the web, no matter it's in text, image, or other data formats, for example, video. And then we want to learn a universal models to get very good representations for different modalities, and then apply this kind of representation to thousands of applications for different downstream tasks. So such as pipeline can be applied to different modality or even cross modalities. But here, our EsViT are mainly focused on focus on the images domain. Before talking about our method, so I would like to call back this figure again. So as we can see here, almost all of these NLP large models actually are using sort of self-supervised learning to learn its own representations and applied this kind of representation to a variety of downstream tasks in different benchmarks like glue, squad, and superglue. So the question to us as a CV people is that whether we can replicate this kind of supervised learning scaling in NLP in CV, so that we can unleash the power of big and labeled visual data, for example, images and videos. Of course, there are some critical ingredients to get a successful recipe. For example, what kind of data we want to use, and what kind of pre-training objective we want to use, and also what kind of network architecture we want to use, transformers or convolutional neural network. So the motivation for us to use the transformer as a backbone is that, so in NLP, transformers actually has been already widely used as we have seen in the previous figure. And the largest model can be scaled up to 1.75 gigabyte. This is very, very huge, or even giant model, right? And based on these transformer layers, they usually use the sentence level contrast learning, that is the next sentence prediction, and also the so-called, I would say it's kind of local dependencies or local learning is kind of mask token predictions. So in computer vision, we also have a large amount of web images, right? And previously we have seen, okay, so CNNs actually dominate the convolution, computer vision domain, and nowadays we have seen, okay, transformers actually are gradually outperforming the convolutional networks around different tasks. And also we have known that the transformer models actually can be easily scaled up to over 1 gigabyte. Then the transformers or CNNs actually in the computer vision domain actually is much smaller. So by this way, we want to, we would like to think, okay, whether we can find a good vision transformer architecture that can be beneficial to the supervised learning, and also can be easily scaled up later. So in comparison with sentence level contrast learning in the NLP, so we also have a view level contrast learning for computer vision for images. So given the different images, we can learn contrast loss so that we can get a good representations for each of the images. And this is pretty similar to the sentence level contrast learning, which contrasts the two sentences. And likewise, if we look at the local dependencies modeling in NLP, so we want to think what's the analogies design for computer vision. Then we think about the local region dependencies, and then we would like to propose some sort of region-based contrast learning. And the second motivation is that previously the vision transformers is just the monolithic one, and now we have seen a lot of multi-scale architectures, including swing, CVT, Vision Longformer, and our focal transformers as well. And we also know that the multi-scale design in one of these transformers actually have show very good performance over the vanilla vision transformer. Then what if we replace this kind of vanilla vision transformer with our multi-scale vision transformer when we perform the supervised learning? Based on this, we present our method, EsViT. So given the input view, we first split the input images, which has two views. One is original view, one is augmented view. We split it into a smaller patches, and then result in longer sequences. And then we perform the sparse attention-based transformer, like for example, swing transformer, Vision Longformer, to gradually aggregating the information and merge the tokens. And finally, at the top layer of the feature map, we just have very few number of tokens which aggregate the information from different regions of the images. And then we perform the cross-view predictions and propose to use a cross-view contrast object functions to learn these representations. And in comparison, the baseline method is just some is just like this. Given orange image, we still have two views, but here we probably has a vanilla vision transformer, and then gradually perform the self-attention, and finally we still obtain the same number of tokens as input to perform the cross-view predictions. And this actually is one of the well-known work Dino. They are doing something like this, and they are using some vanilla vision transformers as a backbone to learn the representations. So based on this, we propose two per-train tasks for our EsViT. The first is view level prediction. And this view level prediction actually is pretty similar to the Dino paper. Given the input, we get two views, and then we have a teacher model and a student model. We extract the global feature for both of the views, and then we use MMP head to optimize, to extract the output probability distributions, and then optimize this kind of cross entropy loss to update the models. And then the second task proposed in our EsViT is that we propose a region-based losses, because for vision transformers, actually there are multiple output tokens, and each of the token can represent a proportion of the input images. And then what if we can further contrast the regions from the first view and the regions from the second view? In this way, we can learn a better localized visual representation in comparison with the original vanilla VIT-based models. So you can see here, given the query region at the first view, and then we found the most matched region at the second view, and then we want to force these two regions to be close to each other in the feature sparse, but far away to the other regions which are not matched to these query regions. And you can see here, this basically depicted our region-based loss in our EsViT. So finally, combine them together, we integrate two losses. The first loss is a view level loss, which basically is this part. And the second loss is a region-based loss, which is basically this part. We combine them together and optimize the model through the supervised learning regime. Before giving more result, I would like to first introduce some intriguing property of the region level object function, which are one of the main contributions in our EsViT. So we all know Dino, and we all know Dino actually show very good properties in terms of their object localization or segmentation. Indeed, when we visualize and perform the alignment between these two views of the same images, we can see here the alignment between the first view and the second view is pretty good. So for example, the point at the first view actually can be matched to very close to the matched location of the second view very closely. But if we do not use any kind of region-based loss and apply the multi-stage or multi-scale vision transformers, then we can see here the alignment between these two views are pretty bad in comparison with the original Dino. Once we further add the region level object into our EsViT, it's still very fast, as faster as this one, because we do not induce much burden to the model forward and backward. We just add an object function on top of it. And in this case, our region level contrast learning will force the model to align the corresponding regions in different views. As you can see here, it's recovered the original very good alignment between different views. And this is just a very interesting property for our EsViT with region level object functions. And then we evaluated the performance for different multi-scale architecture, including Swing, Vision Longformer, and the CVT, and compare it with the ResNet 50 and the DIT. You can see here with the multi-scale Vision Transformer, the performance actually will be improved over the DIT model and also the ResNet 50 model. And then if we further add the region level object function, the performance will be further improved over the EsViT without this region level object function. And also you can see here it's recover the good properties from the original monolithic transformer like the vanilla Vision Transformer. And also finally we quantize this alignment between these two different views of the same images. For Dino, actually, we would say, okay, the alignment is pretty good. And for the EsViT without the region level contrast, then the alignment will degrade much. Once we add them together, then the alignment is recovered pretty well, and also achieve better performance in comparison with the Dino model. So finally, I would like to highlight the efficiency of our EsViT. So first of all, the EsViT, for example, is based on the swing base. If it's based on the swing base, it has 10 times higher throughput than the PERS model like the Moco V3, which uses VRTL for the backbone. And also the model size of the swing base is much smaller than the VRT large. So basically, you can see here with similar performance or even better performance, our EsViT actually has much faster throughput and a much smaller model size. So this basically means that, okay, Vision Transformer, or more specifically, the multi-scale Vision Transformers can help us to learn a very good representations with the Centralized Learning pipeline. And also, we would like to probably explore whether we can further scale a swing-based model, for example, to swing large model, to see whether it can further improve the performance. And finally, we are still topped on Self-Supervised Learning leaderboard on ImageNet 1K dataset with respect to the linear probing evaluation. So finally, we trained the EsViT model on the ImageNet dataset, and then we use this model to various image recognition dataset. For example, here we first use the pre-trained model and then fix most of the model part and just fine-tune the head for different classification dataset. And then we observe that EsViT outperforms the supervised counterpart on 17 out of 18 classification tasks. And this supervised model is is also trained on the image 1K, which uses same data. And then we also compare our method with the clip. So you can see here, the EsViT only used 1.2 million images from ImageNet 1K to achieve 80.99 average scores across these 18 different data sets. But clip used 400 million image text pairs from the web, and then achieved 80.86 across all of these data sets. So which means that our EsViT actually is pretty very effective to learn a generic representations across different data sets and domains. So finally, we would like to show the supervised learning actually can generalize, probably generalize better than the supervised learning. So the first is the self-supervised learning pipeline, and we visualize the attention between the class token and the other tokens inside the regions. And this is the supervised learning. We still visualize the class token, the attention between the class token and the other tokens inside the images. So you can see here it's pretty scattered attention. And it's very hard to interpret, okay, why this class token attend these regions. And this is the clip model. The clip model is performed a little bit better than the supervised learning model, but still it's a little bit worse than the supervised learning model. So which means that the supervised learning model can probably automatically learn to localize the object inside the image. Of course, this has been already demonstrated in Dino paper as well, and it's pretty impressive. So finally, I would like to also mention some take-home messages. So in this paper, the EsViT, we proposed a new self-supervised learning method, use advanced vision transformers, and most importantly, the region level contrast. And it would be worth to highlight that our EsViT outperforms previous state-of-the-art with 10 times higher throughput and 3 times smaller model size. And we can also observe some very good property emerged in our EsViT model, which means that the fine-grained semantic alignment between the regions from different views can be maintained, and also probably can be used as a good indicator to the linked representations or models. To summarize, I guess I do not have more time to introduce more work, for example, the Vision Longformer. So I would like to end up here to summarize. So in this talk, I first discussed about how we can adapt the vision transformers for high resolution images and dense prediction tasks. And we mainly proposed a focal attention for modeling both the short and the long range interactions in the high resolution input. And of course, we have a previous work called Vision Longformer, and it's also used a multiscale architecture design and perform the 2D Longformer on top of the input. And the second work we discussed here is the adaptation of vision transformers for self-supervised learning. Previously, there are some works applying the vanilla vision transformers to supervised learning. We are the first to apply the multiscale vision transformer for self-supervised learning. And also we proposed a region level contrast to enable and maintain the good properties of the self-supervised learning models. So yeah, that's it. And thanks for your attention. And yeah, I would like to take more questions if you have. Yeah, thank you.
Thank you so much, Jianwei. It was a very interesting talk. Maybe we can take some questions. So for me, maybe I can start. For me, it was very interesting that your work on self-supervised vision transformer. I was wondering if you compare with the Dino on the structure prediction tasks, such as segmentation, maybe for more challenging images like Coco dataset, we have complex background. How does it work?
Yeah, yeah, that's a very good question. So we did not try it on semantic segmentation, for example, but we tried it on object detection. And actually the result actually is a little bit mixed. So we observed that the object detection performance with our supervised learning model actually at some times outperform the supervised counterpart and at some time underperform the supervised model if we use different detection method or recipes. For example, 1 time schedule and 3 time schedule, etc. So this a little bit kind of this is also a question to ourselves as well. So from our previous experience, so we know that the model with for example the model with trained with supervised learning method, especially for the ResNet model, actually it's slightly improved the performance of the object detection, but not much. And at the most recently, there's some work like DenseCL, and they're proposed to perform the cross-image region level contrast learning, and then it improved the object detection performance, but it hurt a little bit the image classification performance. So basically, we did not. So to summarize, so we did not observe a significant improvement over the detection task and the image classification task. So we are it's still mysterious to ourselves as well. So why, okay, this model does not work very well or outperform the supervised counterpart on object detections. And we are still studying this aspect actually. So yeah, so we did not try it on semantic segmentation yet, but for object detection, we are still work on it to see why, what's the reason, and whether, okay, there are indeed some kind of mystery things we need to uncover about the self-supervised learning, because yeah, I think a lot of people are interested in this direction. Yeah.
Thank you so much. So we take some questions. Guys, please.
Yes, I have a question. So thanks for the talk. I had a question about your second work. So you showed a slide where you have a matching between two images of a cat.
You mean
you want to bring that slide? Yeah.
You mean
yes.
Which image?
The yellow image, yeah, a bit more. I think
okay.
It's the one before.
This one?
Yes, this one.
Okay.
So
yeah.
you use a SWIN backbone, right?
Yeah.
So I was wondering which features you use to do this matching, like at what resolution or?
Yeah, that's a good question. So for this, we if I remember correctly, so we used alias stage to match the regions, match the tokens between these two input views. Yeah. So basically, I can't remember exactly. So maybe I can reach out there. I can ask the Chen Yuan, the first order again to confirm this. But from my memory, I think we extract the first stage output to present the image and perform the alignment. Yeah.
Okay. And then my second question is a few slides after. So you showed attention maps of like a self-supervised, supervised. Yeah, this slide. So again, like if you use a SWIN backbone, how do you plot this attention maps you're showing for the self-supervised learning?
So this is also a good question. So basically, here because maybe I just made a mistake to describe the first one, the centralized learning visualizations, because for Vision Transformer actually there is no so-called class token, right?
Yeah.
And here we did not use a class token. So I remember that, okay, we used I think we used a nose token to use it as a query token, and then extract the attention for multiple hits. For example, the 6 hits here, and then okay, visualize the attention map. Just choose the top attention scores and visualize this kind of attention maps.
So when you said the top, based on entropy, you mean?
Not the entropy, just the attention scores after software marks. Okay. Yeah. Just visualize the top few tokens. This is basically the
So when you compute the attention, you do it like within Windows. So you're never going to aggregate tokens based on these attention maps, right? Like it's just for visualization.
Yeah. So basically, this is just for the visualization. So we just want to, so compute the similarity between the query token and the other tokens for each of the hit. And we, as you said, so the switch transformer actually is performed the self-attention inside of window, right?
Yes,
yes. But here we just relax this kind of constraint, and they directly compute the attention scores for one of the tokens. So by this way, it's select the top. Yeah.
So it's like a sort of cosine similarity of the tokens of the first stage, and then you probably apply some softmax or something.
Yeah, exactly. Yeah, we just use the same computation as the self-attention. So we just perform the dot product between the query feature for each of the hit and the key, right? And then get the scores and then pass it to the software marks and then get the score and sort it and show the top few tokens. Yeah. So basically this is
Okay, perfect. Thanks.
Yeah.
Thanks, Tim, for the good question. Do you have more questions? Guillaume?
I have one question.
Yes, please.
Great talk, and sorry my camera is off. Can you show the bar chart that you showed in the end one more time, that there was various benchmarks? I just wanted to, yes. I see. So, I mean, these are all classification, just to confirm. Is that correct?
Yeah, it's classification and it's linear probing. Yeah.
I see. Okay. Yeah, that changes a little bit on the question that I was going to ask. I was trying to see whether I can see a trend between classification versus pixelize, like dense tasks versus a structured task versus regression and so on. I see. Okay, then okay, that's all good then.
Thank you. Thank you. Yeah. So, yeah, I think many of you are interested in applying this model to dense prediction tasks like object detection and segmentation. Exactly. Actually, we are also very interested in this direction, and now, we are still working on this. But it's indeed a little bit mystery for us to say that, okay, it does not improve much on the object detection. But indeed, with this region level loss and also the ResNet backbone, we indeed observe a very clear improvement over the supervised model. If once we change our ResNet into a Vision Transformer or multi-scale Vision Transformer, actually we did not observe much improvement. And we suspect there are maybe a few reasons. The first reason is that maybe it tends to saturate for this kind of supervised learning model. And this actually, unfortunately, is not what we would like to see. Because the multi-scale Vision Transformer actually is very powerful, and then probably it's enough for this multi-scale transformer to learn from the downstream data set without any pre-training or self-supervised pre-training with some fancy self-supervised learning method. Maybe it's not necessary. Then this is not what we want to see, because we still believe that okay, self-supervised learning can provide us a very good initialization of the model. And yeah, so we are still exploring this direction and studying the different factors to this result. So yeah, so maybe in the future we can still discuss offline. Yeah.
Cool. Thank you.
Yeah.
Great. Do we have more questions?
Yes, I have one here.
Yes, please, Guillaume.
Hello, John-Wei. Thank you
Hi.
for hi. Thank you for your presentation. I have a question. Do you think that vision transformers are more robust under domain shift than the CNNs?
Yeah, I think that's a really good question. So I have been thinking about this. So in my previous slides, I mentioned that, okay, it's kind of dynamic or it's input dependent computation in comparison with the convolutional features. But I hear from others, for example, the colleagues from my team and the colleagues from other team or even outside the company. So so it's pretty hard to say this. One thing I know is that so it's pretty robust to some sort of adversary type for Vision Transformer compared with the ResNet. So for example, the Vision Transformer is robust to some kind of small occlusions of the image patch. And I think I think there are some papers mentioning about this. And also the conclusion is that if without the fancy augmentation, for example, the mix up, the cut mix, and then this robustness will disappear. So basically, at least I suspect that this robustness is not from the architecture itself for Vision Transformer. It's more like, okay, it's because of the training recipe used in Vision Transformer. For example, the very strong augmentation and regularization. So this probably can help to improve the robustness to the adversary type. But yeah, so I'm not sure whether if we apply this kind of very fancy augmentation and regularization to ResNet, then it still probably have a very similar property as Vision Transformer. So I did not see many works to compare them in a very fair manner. So that's why I cannot conclude anything that, okay, Vision Transformer is more robust to ResNet. So yeah.
Okay, thank you for your answer.
Just to add, it seems there's a recent work in NeurIPS 2021, a spotlight presentation. The title of paper was Integrating Properties of Vision Transformer. They showed robustness to occlusion, adversarial attack, and to some extent to the domain shift. So probably we can also look at that paper.
Yeah.
Right.
Yeah.
Do we have more questions? Okay, so thank you so much, Jian Wei, for the good presentation.